Awesome. Thanks very much. My name's Isaiah, and I'm head of product for core software at Weka. And today we're going to talk about the generative AI versus traditional AI for scaling storage. So let me just restart my timer so I don't fall behind. Sweet. Where did we end up? How did we get here when it comes to storage? The modern AI environment has sort of created a situation where the I/O patterns of traditional machine learning and what we call AI and Gen AI at scale are becoming a bottleneck for getting the high utilization out of the expensive components that we need. We heard Pepe and Siamak talk about this, and I think it's important for us to understand where those bottlenecks are, how we're creating them, and what we can do about them. So today, the real customers that we see have billions of files. They have widely varying I/O sizes, and they have widely varying access patterns. And so what that translates to is that all of the conventional optimization that people did when it comes to file formats and when they were dealing with, let's say, we'll call it legacy parallel file systems, things that you've seen in academia, things that you see in research, like Lustre and GPFS, that sort of thing. All the strengths that they have, the strengths that were geared towards spinning disk, all of those conventional optimizations of large I/Os are less effective when it comes to generative AI. And the reason is because of copying. At the end of the day, we see a huge amount of sprawl with AI and generative AI that is fundamentally based on copying. And so if you look at this chart, there's 8 copies, and this is a diagram from a real customer environment. 8 copies that are being done. And so when we talk about what's waiting on something, all of the time bubbles that Pepe mentioned, that Siamak talked about, those are like nothing compared to these time bubbles. These are enormous. This is like abducted by aliens, forgot the whole day. This is not minutes or microseconds. And so anytime you have to copy data around, you have a data stall. And so what we see is we actually see customers spending like 90% of their time waiting on data to be copied. And so as you think about how your data is being accessed, it's super important to make sure that your GPU is not perpetually waiting for data. And if you're actually looking at your NVIDIA MSI output or something like that, you can see that in fact most of the time your GPUs are going to be idle while you're copying. I mean, it is possible for people to arrange their data in ways that don't result in that, but it is super, super common. So, but everybody has good intentions, and what we see is customers that consolidate their workflows, they bring it onto a single platform. Usually it's Flash-based today, because they know that, hey, I want to keep things in one spot. But then they outgrow their pipeline. And what I mean by that is that they create something called an I/O blender, because the software that's actually providing all of the I/Os for them doesn't necessarily do well with mixed workloads. And so this is the #1 blocker for people who are adopting a generative AI pipeline, because they see that, hey, I'll put everything in on fast media, and maybe they even use local disk. They don't have to use something centrally located. And I'll use a fast protocol and everything will be good. But it turns out that with mixed I/O, not all storage systems handle mixed workloads the same way. So if you have 2 researchers who are working on different things, and the data formats, the data layout that they have are radically different, and they're running their pipeline at the same time, and it's a shared storage system, it's very, very likely that somebody's going to lose. And the person who loses will have less utilization. And when we look at generative AI, it is crazy. It's a family circus journey. And any of these things can repeat themselves at any given point. So the reality here is that each one of these pipeline steps usually has a completely different profile than as far as like what the data looks like. Each one of these steps has a processing component. And when you have GPUs that have different I/O demands to work on the data throughout the pipeline, this means that traditional storage systems will cause you some heartache. So some of these steps need super low latency, random small I/O, whether that's in a life sciences case where you have batches that you're reading from, and you might just be pulling one batch of records out of an arrow file or something like that. Or it might mean that you have some massive streaming throughput requirement where you're doing lots of transforms. We've seen customers that need a concurrent mix of the two because of sub-steps within the process. What the previous speaker was talking about around sort of, when you see the word printed on the screen, it's waiting for that last token. That repeat process happens in a very unpredictable way for storage systems. Storage systems are comparatively simple compared to all of the math that Pepe had on her slide. So as we go through this, I want to make sure that everybody understands that when we talk about a pipeline, we're talking about sort of like a singular pipeline process. And in many cases, we see in real life lots of overlapping pipelines. And so that makes the I/O blender even worse. So this is a customer who was doing NLP. And this I/O, they were doing audio text and audio. And so in this I/O profile, they were doing a pretty significant amount of parsing. And in this environment, we actually see that it's a fully blended mixed I/O pipeline. And we can see that because we have a pretty consistent number of reads with spikes of I/O on writes. And so what we do is we map this information to how heavily loaded our backend servers are. You can do this with any storage system as long as you have the right metrics. And so if we sort of compare the deep purple and the light purple on the bottom, what we're looking at is the CPU utilization. If you zoom in, or if you have good enough eyes, you can see that there's actually lots and lots of spikes. It's not flat. And so what that tells us is that actually this system is only like 5% utilized. And the average, the heavy purple line at the bottom, shows that average. And so this system is really only 5% utilized. And what that means is that this particular workload that spikes up and down with really intense bursts needs a system that can take it from 5% to 100% and come back down and be OK. And most storage systems can't do that. This is a different NLP workload. And if we look at the read and write ratio, not different workload. This is the same NLP workload. If we look at the read and write ratio, you see it's almost 50-50. That you have, over time, you have reads and writes. And you have a lot of variability in the I/O sizes on the reads and less variability in I/O sizes on the writes. And that's really important because what this means is that, for example, in this case, the customer has lots of small samples that are generally like less than 100 kilobytes in size. They're concatenating them together as if they're sort of creating a larger file, and then they're reading against that file as if it were a stream. And so what's happening is you see smaller write IOs are checkpointing what's happening inside of their workflow, and you get a lot of variance as a result in the IO sizes. So when we think about how to service something like this, we can absolutely optimize any of these single pipelines. With any file system almost that has tunables, you can do it. Well, the challenge is when you put them together. This is for a model development customer. And they're building a combination of NLP and other sort of more traditional ML functions. And they have text, and text action. And they're sort of trying to map this to a business application. So their data pipeline is more segregated, and they have a lot less overlap than the NLP use case. They have a lot of, I would say, pretty significant I/O changes during their life cycle. You can see sort of it plateaus, and then it peaks up, and then plateaus again, and dips back down. And that the process of doing that, I should say the implications of them doing that, what does it really mean? It means that they're in the process of ramping up. They have not been able to make their pipeline work to fullest efficiency. And so from a storage perspective, we look at this and we say, this variability in performance for us means that they're absolutely waiting on I/O and they're not compute bound. This is that same customer, and if we look at their I/O distribution, you can see huge amounts of variability in writes and a lot less variability in reads after the beginning part. We would characterize this as probably being a pre-processing phase. And so having if we sort of look at their write ratio, almost 50-50 again. But because there's a lot less variance in the read sizes, I would guess that they would look at their, let's say, how long things are taking. They would look at wall clock time. They would look at how much bandwidth they're consuming, and they would say, oh, this is successful. But our perspective on this is that because they've already done a lot of normalization, most likely, and they've already undergone a lot of pre-processing, and we can see that with the less variability on the read sizes, their pipeline is probably optimized. So when you're thinking about the I/O profile of your pipeline, if you are doing a ton of pre-processing already, or if you are skipping that phase and you're able to actually work against data that's already been normalized, the performance that you get will be night and day. So if you have a file system that is trying to do both, it's very likely that any performance optimizations that you tune for in one will not apply to the other. And so we can see that here for this workload, where we have a subset of a data pipeline. In this case, they're doing almost exclusively an automated training cycle on data that's been ingested that happen to be images. And this is a little bit different than the previous example. But as a storage system, we don't know what your framework is. We don't know if you're using TensorFlow or PyTorch. We don't know what kernel you're running. All we know is that the size of the IOs that are happening, and we need to just do queue management. The more files that you give a file system, the more overhead you have. You can think of it as a tax, and I'll talk about that in a second. And so when we do our measurements for I/O, we're doing measurements for actual data transfer. And it's important to note that if you have a very consistent range of IOs that are happening, for example, on the reads, like in this case, and you have variability in the writes, most likely what you're seeing is you're seeing updates to files, you're seeing write-backs, and you're probably seeing some checkpointing. And so once you start to look at why is my pipeline slow, it's important to be able to characterize these kinds of I/O activities so that you can identify where in your pipeline you're actually seeing your bottleneck. So I mentioned that there was a tax on metadata, but a lot of people don't know how much their tax is. And so for people who have already done this optimization from former file systems to say, you know what, I'm going to have as few files as possible, and I'm just going to do lots of big reads, and I'll read more than I have to, and I'll throw away the stuff that I don't want to. They don't usually experience the kinds of weights that people who don't do a lot of preprocessing do. So the preprocessing can be very valuable, but the challenge is that you don't always know what you need to do. And with generative AI, this is even more muddied. With conventional AI, I think it's super easy for people to be able to say, oh, my gut tells me that I need to do X, Y, Z. But with generative AI, you actually don't know. So you end up with this requirement of a file system that cannot need that kind of optimization. And so we find is that they typically underestimate the amount of metadata load that they're creating. And so what you can see here is we have reads that are, in this case on the scale, it's 1.6 million IOPS. And then we see on top of that another almost 800,000 opens. And people don't think about how their activity in their application actually translates to storage overhead. And so it's super important to be able to think that, hey, I actually could have a tax, and the more files that I have, the more of these opens I'm going to have. And it's not just opens, but I think it's quite meaningful because it's a big part of it. So at scale, what that means is that any one or two steps that are going on at the same time, pretty easy to handle. As soon as you start having lots and lots and lots of mixture of pipeline steps, it's much harder to handle. And so your storage system needs to be able to keep your queue depth quite low. And most of the time, the protocols that you use from a file system perspective, particularly if it's a parallel or distributed file system, need to be sort of acting in a full mesh concept. And this puts more stress on the interconnects. It's then becomes super important that your storage system is doing those RDMAs that skip the host processor. We do all of those things. Most file systems these days that are classified as an RDMA file system, there's only two of them actually, GPFS and us. And if you have an RDMA file system, you get those things for free. But it's super important because if you don't do that, then you burn through all of your write caches in the system. Your performance, particularly your write performance, goes into the toilet. And you end up with this vicious cycle of having to do a lot of additional I/O to refresh the cache. And it results in an overall slowdown of your system. And it extends the amount of time that you actually need in order to complete these metadata intensive stages in the pipeline. So the way that we handle this is we shard all of the metadata services across the cluster because metadata shouldn't be something that you have to tune for. Other file systems, particularly the other RDMA file system, you can't do that. It doesn't automatically tune itself. You need to, an administrator needs to come by and say, let's size these based on our workload. And that sizing based on your workload is great in a traditional AI environment, but as we discussed, in a generative AI environment, you can't do that. And so it's super important to make sure that we have these super even and low queue depths for any metadata requests because it's just going to slow down the actual data requests. So we want to keep those in the 100 microsecond range. And the more granular the data layouts become, the more important this becomes. And so as you think about the data formats that you pick and the frameworks that you use, you might pick something that works great on your laptop, but then as soon as you put it into a shared environment, everything goes away. And so you need to pick the right file system for that as well. When you're building these storage systems, this is a little, didn't quite line up. It did on my laptop. So as you pick your storage system, it's important to note that especially if you're designing one, a lot of people think, oh, I'll just go and design one for my application. And actually, strictly speaking, there's nothing wrong with this. But what we find is that even when it's fast, the network is still the bottleneck. And that's getting better with newer versions of PCIe. We find the network just sort of be in catch-up mode, but it's still the bottleneck. If you have a full mesh system, if you are compute-bound in your storage system, if you're able to squeeze out every piece of I/O that you can from your flash, your network is still the bottleneck. The kernel, in this case, we don't mean your model kernel, we mean your operating system kernel, is slow. And the only way to get around that is to bypass the kernel. And so it doesn't matter if you're using DPDK or on the network, for example, or if you're using UCX. The important part is that you actually minimize the amount of code that needs to be run, because you're competing, just like you're competing in your large distributed system, in your operating system, you're competing with thousands of other threads as well. So you need to isolate yourself and get rid of the contention. It's also super important for the software that's actually doing the on-disk format stuff to actually keep in mind the density of flash is changing and understand how to optimize for that. And then the last part is, how do we make sure that your applications actually don't have to work too hard? And the short answer is that the only way to do that is to place things in a way that are effectively random. But you still need to protect them because over time, with all of these generative AI pipelines, they're still going to require checkpoints. Nobody's going to live in a checkpointless world. And the way that you would recover from a pipeline failure is going to determine what your personal requirements are for how long it would take you to get back up. So it's entirely possible that you might just decide to start over. You're not going to use your checkpoint. This is an okay way to live. You just need to make sure that you have all of your original data. And what we find is that customers mostly do checkpointing. So the traditional MPI-based approaches of having N-to-1 from file I/O perspective, no matter what file system you're using, still create hotspots. But the way to avoid those hotspots is to distribute all of those metadata operations as much as possible. And then it's also important to have these modern features like things like snapshots, because as we probably know, training data not interpolated with most models means that if you have a model in the future, you don't know what data has been trained against it unless you have a copy of that data that you've trained it with. And so keeping point-in-time consistency across training data and the model is important. And you need to be able to, particularly if you're trying to run a business, archive that off somewhere. So all of these things need to be sort of batteries included, and you need to be able to do it in one system. You can't require copies, because as we remember from the very beginning of it, every time you have to do a copy, your GPU is idle. And then perhaps the last part is that caching doesn't work. It's a great optimization, but it shouldn't be part of your architecture. And any attempts that you do to put this into your architecture, ultimately, as your data sets grow, will work against you. And so our solution to that is the Weka Data Platform. We are a parallel file system. We are the data platform for AI. And if you'd like to learn more, I invite you to go check out weka.io. Just as sort of like an easy gnome, sort of like a slider bar thing here at the top, I wanted to sort of summarize that the real AI workloads that we see from a storage perspective, when you have individual ones, you have sort of a characteristic of one type of bandwidth, one type of file size, one type of read and write ratio. But as soon as you get into generative AI, you actually have all of them, and you have them all at once. And it's impossible for legacy storage systems to redesign themselves, unless, of course, they were built with generative AI. So thank you very much, and I would like to invite my esteemed colleague, Dr. Professor Tushar, to the stage.